For our first standard, we have to be able to solve a system in 3 different ways. And we also need to be able to write a system of linear equations to model a given scenario. So if we look at our scale, if you are able to solve a system with 1 of our 3 different ways, that's a level 1. 2 of the ways is a level 2. 3 of the ways is a level 3. And finally, if you're able to do all 3 of the ways and you can write a system and solve the system to model a scenario, then you meet a level 4. The first way that we are going to learn how to solve a system is by graphing. Before we jump into that, let's discuss what a system actually is. You may want to pause the video to be able to write down what's in these blanks. A system of equations is a group of 2 or more equations, and they all have to have the same variables, so x and y or a and b. Currently in this course, we are actually dealing only with systems of linear equations. Moving on into 2b, you may deal with systems of equations that are something other than linear. In order for something to be considered a solution, it has to be a point that makes all of the equations true. So if I took that x value and I took that y value and I plugged it in for x and y into both of the systems, I should get a true statement no matter which system I'm using, no matter which equation I'm using. If you flip it over to the back, you'll see this table. We are going to only fill in the top of this table right now. So once again, you may want to pause the video to be able to fill out this table. As far as the graphs go, I'll move them up in just a moment, but these graphs do not have to be exactly on the exact points that I have. They just need to look similar. So we have 3 different ways that a solution could appear. We could have a solution where there's one solution, and in this case only one point would work in both of the equations. We write that solution as an ordered pair, so it's written as a point, x comma y. And then when we are graphing it, we are looking for the point where they cross, because I know that that point will work in both this line and in the other line. For infinitely many solutions, or IMS, that would be any point that's on one line would also be part of the solution to the other. And what happens is it's actually the same equation, it just looks different. Think of like equivalent fractions, 1/2, 2/4. Those look different, but they're actually the same fraction. That's kind of what's happening here in this system. We use IMS to represent infinitely many solutions. And when we graph it, it just looks like one single line because it's the same equation. The third kind of solution would be actually no solution. What happens there is that both of the equations are going to have the same exact slope, but different y-intercepts, which will make them parallel. And so there won't be a point that's in common to both equations. So parallel lines would be no solution. Finally, we should be able to describe our systems. When I talk about describing our systems, we are going to be talking about naming them as consistent and independent if there's one solution, consistent and dependent if it is infinitely many solutions, and then finally we have inconsistent when there's no solution. Let's jump in and actually look at what it would be like to solve a system. So I have a system that's already been graphed here. With this picture of Star Wars, the lightsabers make up the 2 lines that are going to cross or be our system. So the point that those cross at, right here, is going to be the solution to our system. So here's Darth Vader's equation, here's Luke Skywalker's equation, and the point where they cross is at -1, 2, 3, 4. and then down 1, 2, 3, 4, 5. So that's how we would write a system solution if there was one solution. Now, of course, it will not be that easy for you guys. It's not already going to be graphed for you. You are going to have to do the graphing. I'm going to show you two different ways. One way is the way that you guys are all used to, and it can always be the fallback if you get to the quiz or to the test and you have forgotten how to use your calculator with it. But solving a system of equations by graphing without the use of a graphing calculator, you would first rearrange the equations, both of them, so that y is by itself. Then you're going to identify your slope and your y-intercept. Then you will graph each of those equations on the same coordinate plane, just like we saw with the picture of Luke Skywalker and Darth Vader. Finally, we have to use a straight edge to connect your dots. Do not try to freehand these, even if you're using your graphing calculator. You need to use a straight edge because without it, you don't know if it really will go through those 2 points. And then finally, our point that they cross at is our solution. So let's walk through a problem where we're doing that kind of by hand method. If you turn it over, number 1, we have two equations here that make up our system. I'm going to do the first equation in orange. So we have 4x minus y equals negative 11. I'm going to graph it just like I learned back in chapters 1 and 2. I'm going to subtract 4x from both sides to get y by itself. Oops, I wrote y, but meant x. So I'm left with negative y equals negative 4x minus 11. Then I'm going to divide by negative 1 all the way across, which gives me y equals positive 4x and positive 11. So our slope would be the number in front, 4, or since we're using it as slope, we'll write it as 4 over 1. And our y-intercept comes from the 11, so it'll be 0, 11. And I know that if you've counted this, you've only counted 11 or 10 little spots, but 11 is so close, it's just one off. I think you can estimate where 11 would be. So we'll take 11, and of course we don't have any room to go up 4 and over 1, so I'm going to need to do the opposite. We'll go down 1, 2, 3, 4, and left 1. I really recommend that you guys do this all the way across if you are choosing to do these by hand. Especially if you have to graph on GoFormative or any other kind of electronic platform or virtual platform, because if you graph only a couple of dots, you may not have an exact line by the time you get to the other graph because your dots are just slightly bigger than the exact point that you're plotting them on. The same can really be said on paper, but we can be a little bit more exact because our pens and our pencils are pretty small in their line. Now we're going to do the same process with the blue equation, or the second equation as it is. So we will subtract 5x from both sides. We have 2y equals negative 5x minus 4. Then we will have to divide by 2 all the way across so that we have y equals negative 5 over 2x minus 2. So our slope is negative 5 over 2, and then 0, negative 2 is our y-intercept. So we'll start at 0, -2. And then we will count down 5 and right 2. 1, 2, 3, 4, 5, right 2. I don't have room to do it again, so I'll start back at my y-intercept and count up 1, 2, 3, 4, 5, and left 2. Now, if you plotted all of your individual points, you should find one of the points from the other line coinciding with the point that you're plotting. This will happen every single time that you are supposed to get an integer or a nice non-decimal answer. I can't promise that they will all be non-decimal answers, but the majority of them should be. In Algebra 1, when you did this, they all had to be non-decimal integer answers because this was the only tool that you had in your toolbox. -2, 3 is my solution. But now we have the use of our graphing calculator. We can actually find decimal answers for our systems using graphing. So when you are graphing on your graphing calculator, there's a few steps that you're going to need to follow, and you're going to get really good, hopefully this year, graphing on your graphing calculator, but this will really be kind of your first exposure. So make sure that you get these written down. First, you have to rearrange your equations so that y is by itself. Then we're going to press y equals. And make sure that your plot 1 is not highlighted. None of the plots should be highlighted when you're graphing just a regular equation. The only time that you have a plot that's highlighted is if you actually want to see the individual data points that you inputted into STAT. We're not doing that in this section, so we don't want the plot highlighted. If it is still highlighted, use your arrow keys to get to the plot and then press Enter to make it not highlighted anymore. Then we will type the equations into y equals. So it'll be into y1 and y2. And to get the x in your equations, you're going to locate the x, t, theta, n button. It's right next to your alpha key. It should be green on your calculator. The alpha key is green. Once you've got your equation put in there, if you use zoom and select option 6, it will put your window back to what we call a standard window. That means that the minimum value for x and y would be -10, and the maximum value for x and y should be +10. And it'll be counting by 1. Now that's not always going to be exactly what you need for every single graph, but it's a great place to start. If you go to graph and you can't see your equation or you can't see where they cross, you may need to adjust the window manually, and you do that by actually just pressing the window button, just like we did with linear regression. And just manually change your x and y values to be a bigger window or a smaller window so that you can see what you need to see to answer the problem. Then we are going to use the table function to plot your points. To get to the table, just as a reminder, you're going to press second and you're going to hit the graph button. It says table right above it. Once you have gone to the table button, plot all of the nice points that you see that will fit onto your graph. Don't worry about trying to estimate the decimals unless there are no other integer numbers to plot. Now to find the exact intersections, because it's not enough to just trust that that's where it crosses, because like I said, it may cross at a decimal. So to find the exact intersections, we are going to press second And then the trace button, it's also along the top. Trace says calc right above it, and that's what we're trying to do. We're trying to calculate what the intersection is. And we will select option 5, which is intersect. Once you've done that, you're going to use your left and right arrow keys. Do not use up and down. All that does is move from y1 to y2, so from one equation to the other. Left and right arrow keys to move your cursor close to an intersection, and then you're going to press enter. Make sure that your cursor is still pretty close to the intersection, and you're going to press enter 2 more times. It will pop up along the bottom of your screen. It'll say intersection, and then it will say x equals, and then y equals. Make sure that you write that as a point with parentheses and a comma in between the numbers. We don't want you to write x equals a number and y equals a number. Let's go through this process for number 3. So we're going to solve to get y by itself. Subtract 7x from both sides. And we get negative 2y equals negative 7x plus 4. If you haven't yet learned how to do those literal equations and getting y alone, now is an excellent time because you're going to need to be able to do that to graph. Then we'll divide by negative 2 all the way across. So 7/2 x minus 2 is our first one. And we need to do the same thing for the second equation. So we'll subtract 12 from both sides, leaving us with 6y equals 3x minus 12. And then divide by 6 all the way across. Now here, up until now, it's the same as whether we were doing it by hand or using our calculator. And it's always a good method. If you want to go ahead and try it by hand, then you can always use it by hand and find your slope and your y-intercept that way. A lot of times it's faster, just sometimes it's not. And sometimes we're forced to whenever we get a intersection that's not an integer. So we go to y equals. We're going to enter in this equation, the orange equation, into y1. So 7 over 2, and then x t theta n. That's what this button is right here, right next to the alpha button. That puts x into our equation, minus 2. And then our blue equation was 1/2 x minus 2. And so if we hit zoom in 6, it'll automatically graph it for us. Please do not just look at this graph and estimate where it is. We do need individual plotted true points. So it looks like my window is doing okay. So we'll press second and then the graph button, which is the table. And here we can see all sorts of all sorts of points on our table. Now your calculator, especially coming off of the test, may be set to something that's pretty large. You have a couple of options. You can use your arrows to get down to something that would fit onto your graph, or you can use second and table set, just like we did in the final standard of chapters 1 and 2, and tell it to start back at something that will fit on your graph, like 0. And then go back to your table, second table. So you can see there's my y1, or my orange equation, all of the points. And I'm going to pick a few of those points to plot on the graph. I only need to deal really with the ones that are nice and pretty and that will fit on the graph. Like, for example, when I get to -5, obviously negative 19.5 is not going to fit on this graph. So the first one it looks like that will fit nicely is at -2 and -9. And I'll just move from there. Okay, those are the only ones that are really going to fit nicely on my graph. So I'll draw a line in between them. And for my other equation, my blue equation, I'm looking at the x column and the y2 column. So I can see that -9 and -10 will both fit for the y, but I'm now way off of my graph for the x. Just find the ones that will fit. So 10, -10, and -7 will fit. And we can see all of the points on here are just the same ones that I plotted here, just the nice ones. And draw our line. Now we're going to find the intersection. You should be able to, because like I said, most of our answers are nice, pretty integers, but you should be able to tell the intersection at this point because we plotted for both of them. We plotted the point at 0, -2. Let's confirm that on our graphing calculator. Again, just like in the beginning when you had easy equations and you were learning how to solve equations, you had equations that you could do in your head while you're learning so that you could check them. That's what we're doing now. We're learning how to use our calculator so that we can check it without our calculator, so that when we have a problem that must be done on our calculator, we're already comfortable with it. So we're back to our graph, and we're going to press second and calc and select option 5, intersect. It's going to ask you some questions down here, but I already told you what you're doing with them. You're using your left and right arrow key to move close to where they cross. Well, this just so happens that it's on where it crosses, and we'll press enter. It's still near where it crosses, so I'll press enter 2 more times until it says intersection 0, -2. And that's the point that we'll plot. Let's do a couple of more. So 2x plus 4y equals -16. We'll subtract 2x from both sides. So I have 4y equals -2x minus 16, and divide by 4 all the way across. And that leaves me with y equals -1/2 x minus 4. The other equation, x plus 2y equals -8. We'll subtract x from both sides. We have 2y equals -x minus 8. Divide by 2 all the way across. And y is equal to -1/2 minus 4. negative 1/2 x minus 4. Now, this should be very, very, very familiar to you. You have two exact same systems. So we already know before we even plot it that we should have something that's IMS, infinitely many solutions. You need to prove that though by showing what the graph looks like because the standard is asking you to solve by graphing. So again, we can use our calculator to get those points just to get a little more practice. So y equals, I'm going to clear out what's there. I don't really need to put anything into y2 because again, they're the same equations, but it's certainly okay if you do. So negative 1/2 xt theta n minus 4. And we will hit zoom 6. There's what our graph should look like. My window's okay then. And we'll go to our table and we'll get some points. So negative 10 and 1. And even if I were to graph the blue equation, I would end up exactly in the same spot. I mean, since I'm using two different colors, why not? I'd end up exactly in the same spot. My answer is IMS. How about this one? We'll use the first equation as our orange equation. We'll subtract 10x. Divide by negative 4. And y is equal to positive 5 over 2x positive 3. Let's solve to get y alone in this equation. We'll subtract 5x. Negative 2y equals negative 5x minus 10. Divide by negative 2 all the way across. And y is equal to 5/2 x plus 5. Now again, if you were paying attention as you're walking through this problem, you would maybe notice that these both have the same slope, which means they're going to be parallel to each other, which means we should have something that's no solution. Just to make sure we're getting some practice on our calculator though, we're going to use our calculator to find the points to plot. So we'll enter in 5/2 x plus 3. And then in y2, we'll do 5/2 x plus 5. Zoom 6. So we can see that I have two parallel lines. So we know that if I were to try and do second calc and do intersect, option 5, there's not really a place that they're going to cross, and it's going to give me an error because of it. It'll say an error, no sign change, which means that we have got something that's no solution. But we can find some points from our table, second table, find some that will fit on your table, and plot them. Personally, I find that plotting with the slope and y-intercept is faster than the table, but we won't always have that option because we will be graphing lots of other different kinds of functions. So it's always a good idea to get a better handle on how to use that table function. And since they're parallel, we would say no solution. Now remember, we can also describe each of these systems as, according to our table there, consistent and independent, consistent and dependent, and inconsistent. If it has one solution, we would say that this system is consistent and independent. Since this one has infinitely many solutions, we would say that this system is consistent and dependent. And since this one is no solution, we would say that it is we would say it's inconsistent.